Okay, so alright, so we're going to be looking at not sure what's going on here. Okay, so this is Unit 2, Lesson 6, and we're going to be looking at what we call Bohr models. And this is very simple, so I'm not going to spend a lot of time on this. Again, you have to remember that the Bohr model, remember again, is not the actual model of the atom. The actual model of the atom is the quantum mechanical or electron cloud model, but we still use the Bohr model because it's just plain simple. If you look at it, they tell you to use a square. Here's what I'm going to have you do. When they ask you, or if you're asked to draw a Bohr diagram, and you'll see this a lot when we do the unit on bonding, put a circle to represent the nucleus. Now, in the nucleus are the protons. In the nucleus are the protons. One more time. In the nucleus are the protons and the neutrons. So protons would be P with a plus, neutrons N. Okay, I don't know why this is doing it again. I guess I should figure it out. There's the nucleus, protons, neutrons. Okay. Now, oxygen, if you look at the periodic table, has a mass number of 16, atomic number of 8. So it's going to have, as it says here, 8 protons, and to get the neutrons you subtract, so it's going to also have 8 neutrons. Now what you need to do is to figure out how many energy levels, because that's where the electrons are found. It actually tells you in the configuration. Now notice that oxygen has 2 numbers in its configuration. That means that it has 2 energy levels, principal energy levels or orbits or shells. You don't even have to draw full circles. Now they tell you to put X's or dots to represent the electrons, but I think what you can probably do is simply just put the numbers. So there's 2 electrons in the first energy level and 6 in the second energy level, and that would be the Bohr model for oxygen. Let's take a look and do a couple of different ones towards the bottom, as you can see here. I'm not going to do all of these for obvious reasons. So we'll do carbon. Now carbon is 12 over 6, and its configuration is 2-4. So the nucleus is going to contain 6 protons and again 6 neutrons. And it's going to have 2 energy levels. There'll be 2 electrons in the first level. I'm going to draw a half circle and 4 in the second level. For fluorine, which is 2-7, it's going to have 9 protons, and it is, I believe, 19 is the mass, and the atomic number is 9, so it has 10 neutrons. And it's going to have, and I'm going to draw half circles, 2 in the first level, 7 in the second. Now, I'm going to skip over and do sodium. Now, notice it has a plus. So now, if you look at the configuration for sodium, it's 2, 8, 1. The plus means that you then now get rid of that electron. So its configuration, the nucleus will be the same. It'll have 11 protons and 12 neutrons. But now, instead of having electrons in 3 energy levels, it's only going to have electrons in 2. It'll have 2 in the first and 8 in the second. Sulfur, on the other hand, is 2, 8, 6. The negative 2 means that you now add 2 to that to make that 8. So now your nucleus, that doesn't change the nucleus. You're still going to have 16 protons, and I'm just going to write this, 16 neutrons. But if you draw the Bohr model, it's going to have 3 energy levels, and it'll be 2, 8, and 8. And that's how you do more Bohr models for elements, for atoms, and as well as ions. And let's go down to the next section, which is what we call Lewis dot diagrams. Now, Lewis dot diagrams is something extremely important. We use it, not only do they ask you to draw them for elements, but it's also part of what we will look at when we do, for example, bonding. They're also very easy, and they are also related to the configurations. Basically, an electron dot diagram, or a Lewis dot diagram, is you take the symbol of an element, and then you place dots around the symbol that represent the number of valence electrons. So, for example, if an atom has 5 valence electrons, you would put the symbol and then put 5 dots around it. There is a specific way of doing it about how to put the dots, but honestly, on the Regents exam, they really don't care as long as you get the correct number of dots. Here, they're trying to show you how to put the electrons in. These are two different ways of doing it. I'm just going to go through and show you some examples because I just think it's just so easy. Why complicate it with that thing? And I'll do this as an example. If you look at the element carbon, carbon has an electron configuration of 2-4. Now you notice how they give you two different possibilities. I prefer this one. So basically what you say is, okay, carbon has 4 valence electrons. I'm going to start at the top and work my way clockwise. So that's my first electron, my second electron, my third, my fourth, which is all I need. Now, what about if it had 5? I would put a second one here. If it had 6, I'd put another one here. And that's basically how you do electron dot diagrams or Lewis dot diagrams. And again, I'm not going to complicate it by looking at the orders and stuff like that. I think it's so easy. I really don't think that you need to spend a lot of time on it. Now, here's where it gets tricky. You can also do dot diagrams for ions. So, for example, if sulfur has 2, 8, 6. So it would have here sulfur. It would have 1, 2, 3, 4, 5, 6. But when sulfur becomes an ion, it gains 2 electrons. So now you would have to put 2 more electrons. Now that it's an ion, then you have to put brackets around it. And then indicate that it is a -2 charge because now it gained 2 electrons. Same thing with potassium. You don't really need the brackets for potassium, but its configuration is 2, 8, 8, 1. What that means is that means it lost 1 electron, so you do not include that. So what happens is, here's K. It originally had 1 electron, but it lost it. So that electron no longer exists. So all you would write is K and then the +1. You do not need the brackets generally for a positive ion. So you need to be able to write electron dot or Lewis dot diagrams for both atoms and ions. And let's see if we have a couple of examples. Oh, I knew we would. Alright, so let's do these. So let's do argon. Let's do phosphorus because it's 2, 8, 5. So phosphorus is P. So it has 5 valence electrons. So it's 1, 2, 3, 4, 5. So the electron dot or Lewis dot diagram for phosphorus has 5 dots around it. It has 2 paired electrons and then 3 unpaired electrons. Silicon, I believe, is 2, 8, 4. It would be similar to carbon. We'd have 1, 2, 3, 4. I'm going to skip around. Let's do nitrogen with the -3. So now nitrogen, which is normally would have 2, 5. So it has 5 valence electrons. 1, 2, 3, 4, 5. But the -3 means that you need to add 3. So I'd add here 1, 2, 3. Then I have to put brackets around it and put the -3 here. Sodium, on the other hand, has 1 valence electron. But that means that it loses it, right? Here's the configuration, 2, 8, 1. It loses that electron, so it has no valence electron. So you'd simply put the brackets, and you don't really need the brackets. And +1. And you don't really need to write 1. So a couple of things, if you look at the bottom, that it talks about, which are important. And you'll see this when we do bonding. The number of unpaired valence electrons is equal to the number of bonds that an element can form, and we'll talk about that later on. Carbon can be arranged in either of 2 ways, and we talked about that before, but we're going to look at carbon in this particular